Okay, my name is Guillermo Toriz, and today I will be giving this lecture about the surface chemical analysis of materials. And of course, this is within the surface engineering course, and I will be talking about these spectroscopic techniques that are related to the analysis of the surface. So the first one is the secondary ion mass spectroscopy. The second one is X-ray photoelectron spectroscopy, and then is Fourier transform infrared spectroscopy, and finally Raman spectroscopy. And well, why surface analysis is important? And as you can see, is the surface of materials that really in many times drive the applications and the performance of things. For instance, in semiconductors, you can see this as patterned thin films. In magnetic media, you can see nanometer protective coatings. And for the materials research, we see that this is used in metal alloys, glasses, ceramics, and polymers. And then speaking about polymers, you can see the surface modification of polymers for adhesion and also for the delivery of drugs and packaging. And of course, thin films and coatings in windows for self-cleaning. And then the biomedical applications. And basically, this is it's very important for metal and polymer surface in correlation with biocompatibility. So surface analysis is quite important because the uttermost atomic layers of a material plays a role, a fundamental role to the final properties. So this role is affecting the chemical activity, adhesion, wettability, the electrostatic behavior, corrosion, and biocompatibility, and so on. And also, in many processes, these chemical analyses are useful to identify the failure of products like stains, defects, contaminants, the diffusion of products and impurities at the surface of a solid or a sample, at interfaces, and so on. Of course, through these techniques, we can have a quantitative composition of the surface, mostly after surface modification or after cleaning the surface, or also for the detection of residues after some processing. This cartoon shows what is the surface, and I like it very much because we can see here that the top surface, the technique that is most used or the most useful probably is the one that is very simple and economical, like the contact angle. However, it has a big drawback because at the same time as it gives you some information or a lot of information that is basically on the surface, on the top surface, it's very difficult to interpret. So contact angle is very important and it's simple and it's cheap, but it's difficult to interpret. And then we have the atomic force microscopy, and in general the scanning probe microscopy, like the scanning tunneling microscopy and so on. The static secondary ion mass spectroscopy is also looking at the top layers of the material. And then the first 10 nanometers, you can see them with electron spectroscopy for chemical analysis, that is also known as XPS, X-ray photoelectron spectroscopy. So you see that ESC and Auger that usually come in the same instrument. And then you can see that also the attenuated total reflectance spectroscopy infrared spectroscopy, it's useful to see the surface of a material. I will go more in detail in the next slides. But as I say, you can see these techniques, you can use them to check failure in materials, like for instance, crack, defects, and also to look at the adhesion in commodities like diapers, baby diapers, and also the surface modification on different biomaterial applications. We used to have a strong program on the surface modification of lignocellulose, and specifically on cellulose and hemicellulose. And these materials are quite important in Scandinavia because of the great source of forest that you guys have over there. But so all these commodities need to, up to some extent, the modification on the surface to improve several characteristics or to impart them, like high wet strength or low wet strength. And then printing on polymers that usually um, are difficult to be printed on because the nature of the materials usually rejects the interactions. So then the modification of materials are useful to improve this adhesion. And as I said, packaging, drug delivery, and also the multi-layer packaging. Tetra Pak is worldwide, everywhere. It's everywhere. And the multi-layer is polyethylene and then cardboard, lignocellulose, aluminum foil, and polyethylene. And it's difficult to keep this material together because they don't like each other. So how can we analyze this? We have tons of different materials, but probably it's useful to look at these acronyms. There are many kinds of spectroscopic methods, and you can see here, for instance, ATR, it's attenuated total reflectance, and so on. You see diffuse and ion scattering spectroscopy. So we will focus on secondary ion mass spectroscopy and the X-ray photoelectron spectroscopy or electron spectroscopy for chemical analysis. And all the other acronyms, you can look at them, but you see ultra high vacuum and ultraviolet, infrared, and so on. So why there are so many different spectroscopic methods? Because they give you different information under different conditions. So you can see here, like for instance, the ion scattering spectroscopy, the first one. It gives you the element surface composition on materials, and it gives you some quantitative information. And you can see the first two layers. This is not giving you depth profiling, so you cannot go within the material. And so therefore it's a real surface sensitive technique. And then the static secondary ion mass spectroscopy, it gives you information on surface functional groups, and we will go in more detail in the next slides later. It can give you some quantitative information, but it's difficult. It's not possible to do depth profiling. For that, you can use dynamic SIMS, but we will see later also. Then the XPS, you can give you the surface elemental composition and functional groups. It's not difficult, and you can get a lot of information. I like that technique particularly. I used to work. I work a lot with that. It gives you the depth profiling. It depends on the angle in which the X-rays are applied, and then the layer in normal mode is from 4 to 10 nanometers. So I would say that is surface sensitive. And then we got all these vibrational spectroscopies that I'm not so sure is so surface sensitive, because it goes from 1 to 10 micrometers, more or less, even 1 to 50 micrometers. And some others go into the whole material, into the bulk. So it's, but nonetheless, you can also get some information, especially for comparing if you have a modified surface. I would like to point out that the surface enhanced Raman spectroscopy is also quite surface sensitive, but this is surface enhanced, and we'll see how this works. It's semi-quantitative. So in general, I would say that you can get quantitative information on the surface, but you have to be careful, and then you have to try to use some other techniques to confirm your findings. And then you can also compare these techniques in the way that you analyze the different materials. For instance, the ion scattering and the secondary ion mass spectroscopy and XPS, you need ultra high vacuum. It's important to have high vacuum, because otherwise the information is lost in the medium. So you need that the electrons can fly and be detected and then not sorted and so on. But then you need ultra high vacuum, and ultra high vacuum is 10 to the minus 9 millitorr. It's quite high vacuum. Also, you can expect in this ultra high vacuum analysis to have a slight surface damage. Is sometimes it's not seen unless you damage the surface on purpose to see the depth profiling. Otherwise, is no problem. And then the infrared spectroscopy doesn't damage the sample, and it doesn't need really surface preparation. Of course, all these samples need to be free of humidity, or free of moisture, and of course is important. For instance, in nuclear magnetic resonance, you need to rotate the sample, something like that. And in transmission infrared spectroscopy, the powders must be compacted, and also they must be immersed in some kind like matrix of potassium bromide. So here we go. Increasing the increase of the depth of analysis depends on what you are using. If you are using ions, it's on the top, and then the next level is electrons, and then photons like UV and infrared and radio frequency. You're going increasing the depth of the analysis. And of course, this is mass spectroscopy. So in the first one, the RBS, which is Rutherford backscattering, and secondary ion mass spectroscopy, and ion scattering spectroscopy, we need a mass spectrometer. And what you need is, of course, to have free atoms or molecules in the gas phase, and they must be, or they have to be charged, because what we measure is the mass with the valence. or divided by the valence. And then the ways to achieve this is by thermal desorption, field emission, laser ablation, electrospray, electron impact, chemical ionization, plasmas, matrix-assisted laser desorption, ionization, and so on. So then we go here, secondary ion mass spectroscopy. And what happens is that a solid sample is bombarded with primary ions. And you can see primary ions with an energy from 1 to 50 kiloelectron volts hit the sample, and then they eject secondary ions here. And these secondary ions can also, you can eject also ions, molecules, fragments, or atoms. So basically, we bombard with primary ions, and the fraction of particles emitted from the target surface is ionized and analyzed with a mass spectrometer. And then you can see that basically what we are doing is sputtering. And basically, we have primary ions which are bombarded to the sample, and they generate basically two processes. They are called primary and secondary recoils. And the primary recoils cause sample damage through ion track, and then also primary ions are implanted in the material, and the secondary recoils make this particle emission from the surface, and these are things that are sputtered, and of course there is some surface damage. And you see here, this is the path of this primary ion that goes in different processes, and then some particles are sputtered, are ejected from the material, and these are atoms and clusters and molecules and neutrons. So what we can say here is that if you want to run this technique, you have to keep in mind sputter yield, secondary ion yield, and these things are important because the sputter yield are the removed particles divided by the primary ions. And of course, it determines the limit for non-destructive analysis. And then the secondary ion yield depends on the ionization energy and the matrix effects, and of course, makes quantification possible, but it's also difficult. So, if you have a large number of secondary recoils with low energy, you limit the emission depth to less than 3 monolayers. So you're looking only to the surface. You can also look at the diameter of the excited region, and it goes from some tenths of nanometer to 10. And of course, it depends on the binding energy. And then the low energy distribution, of course, influences the mass resolution. Then you can see here different figures for secondary recoils. So what can you use for SIMS? It's liquid metal ion guns. The focus is less than 100 nanometers, which is very good. And then you can use gallium, gold, bismuth, and cesium. And the first three are ion sources that gives you different characteristics, like gallium gives you high focus and intensity. Gold gives you high sputter yields, and good focus. Bismuth is at this point, a couple of years, it was the state of the art. And cesium enhances the negative sputtered yield, sputtered secondary ion yield, but has poor focus. So this is for liquid metal ions, and for electron impact guns, they have poor focus, and then you can have argon, oxygen, carbon 60, and argon clusters. And it gives you different purposes. Like argon is for depth profiling, ion etching, and secondary ion yields are enhanced for oxygen plus, and for large molecular ions, then you can use C60 plus. And if you get argon clusters, you get soft sputtering, and then you can have a good yield for large molecular ions. So if you want to make a depth profiling, then you can use dynamic seams. And these dynamic seams is basically etching the surface and giving you the composition through the thickness of the sample. But then you need a high primary ion intensity. You will damage the sample, and then the analysis is continuous as the depth is increased. So you can have the applications are bulk analysis, the depth profiles, for instance, for surface films, and then the elemental imaging, for instance, grain boundaries, trace elements, and so on. And the new developments are ion guns for softer sputtering and for molecular depth profiling. In the static sims, the PI dose is low, and then the one area is hit only once during the analysis, and the analysis is always done in a pristine area. And for instance, you can remove in a monolayer 10 to 14, 10 to the 15 atoms per square centimeter. And the primary ion dose density is low, is less than 10 to the 13 ions per square centimeter. So if you have an analysis area of 100 times 100 square micrometers, you have a primary ion current of 1 picoampere, and the time is 10 to 100 seconds. And if it is one order of magnitude lower, 100 micrometer squares, then it's 1/10 of picoampere, and the time is also 1/10. The detection limits, you can form up to maybe 10 to the 6, 1 million secondary ions form in those examples, and 10,000 ions. So, of course, the static SIMS requires a mass analyzer with high transmission, and this can be enhanced with time of flight analyzer. So this is an example of positive and negative secondary ion mass spectra for polyethylene, and you can see here this is polyethylene, and polyethylene, the repeat unit is CH2. So CH2 means 14 atomic mass units. And since in the positive, you can see here, we add 1 and it's 15, and then plus 14, plus 14, plus 14, plus 14. So it's giving you the fragments that you are analyzing with the material. So basically, you have chunks of this polymer in the monomer is shown every 14 units, as you can see here. From 15 plus 14 is 29, plus 14 is 43, plus 14 would be 57, which is this small peak here. Remember, we are uh, extracting different um, ions, atoms, and clusters, and so on. So this is in line with the composition of the polymer. For the negative spectrum, you see less, I would say, less accuracy, or smaller fragments. If we see the time of flight secondary ion mass spectroscopy, you can see here a much nicer spectrum. And as it says, the spectrum is dominated by saturated fragments separated by 14. So how does this work? The time of flight mass spectrometer, you see that we have um, a pulse ion or laser beam, and then the sample is held here, and then we have here some electrodes for extraction, so there is a potential here, and then this is the flying path, and here there is an electrostatic reflector, and then the ion detector, this is deflected, and then the ions go here, the signal, and then goes to the spectrum. So you can see all these details in this literature. But basically, you see here that the TOF spectrum, these constants are calibrated by known masses. So mc n divided by z, it's equal to a times t times b. And of course, t, you see the energy is the kinetic energy is constant from acceleration field. So, and then we have here the energy times the balance, and then the flight time is the length divided by the speed, and then we can just plug this in here, and we can get this calibrated. So the advantages of a time of flight analyzer is that you have a parallel detection of filtering, so it's very good, high transmission. You don't have any mass range, but basically you can be limited by ion formation and ion stability. And then there is high accuracy, which is dependent on the calibration, but it's not bad. Absolute mass error typically is 10 to the minus 3 atomic mass units for less than 100 AMU. So the relative errors are in the range of 10 parts per million. We get high mass resolution and more than 10,000 single mass resolution, which means that is more than 10,000 Daltons. So the time of flight secondary ion mass spectroscopy, just remember you have pulse ion gun, you are in ultra high vacuum, and then you apply this energy. I mean, I'm sorry, you get these sputter or ejected ions, and then you get them here in this analyzer, and basically an enlargement of this area is here. You get the primary ions, and then you get atomic ions or molecular ions, and the thickness of the analysis is just less than 1 nanometer or 1 nanometer. So the time of flight is a method for mass filtration. So here we can see some examples. This is polydimethyl siloxane. So here silicon is, I think, is 28, and then we have here methyl, so it's 1530 plus 28 is 58 plus 16, 58, 68, 74, 74. So here you get here the probably some fragments. I was thinking of this SiCH32O. So in this material you can see the repeat unit of polydimethyl siloxane, and this is the positive spectrum. And then in polystyrene, you see here the mass that is C7H7 at around 85 and 95 M divided by Z, so the mass. And here C3H2, which means 36, 38 around here, C4H3. So you need to know more or less the structure of the material and then correlate with you're looking at the surface. In this example, we have polyethylene terephthalate. This is the repeat unit. And you see here that this fragment weighs 193, and that this fragment from here to here, well, this from here to here is 149, the orange one, and then the blue one has 104, probably is, this is 12 and 16 is 28, so it must be somewhere here. And then this is 72 plus 6 is 78, so must be somewhere here. 78 plus 28 is 100, so 104. So this is the different fragments. You can find them in the secondary in this with this technique. So why do we do this? So we want to see if the surface is different from the bulk. So in the surface analysis, we want to know what elements and compounds are on the surface, and if they are not there, what are these in contaminants or impurities, and if they are distributed over the surface, and how, and if they go into the material. So the major challenge is, of course, to see the difference between the surface and the rest of the material, and then we're looking at minute amounts of materials, very very small amount. So it poses some questions. Are we really seeing something real or artifacts? So for the static seams, I will repeat, high surface sensitivity. We can see all the elements, including isotopes, molecules. If we have a high mass resolution with TOF, for instance, we can have detailed chemical information, and we have very low detection limits. We can also have imaging, and then we have a submicron lateral resolution. We can analyze composites, particles, fibers, and microfabricated materials. And then we can see imaging of lateral distribution at surfaces or in cross sections. So for the chemical images, basically you can superimpose different materials and then see them separately and then put them all together. So the idea is to focus primary ion beams over an analysis area, and then the spectrum shows what substances are present on the analysis area, and then we can combine and construct images and see, overlay them and see what different materials are there. And you can see here ion imaging from microstamped CH3 and COOH terminated tiles on gold. And these are 40 and 60 micrometer stripes. And as you see here, this is gold, and then you see here this is terminated with CH3. I think this is a mistake. And then this is with carboxyl groups. So basically, this would be quite interesting. And I'm gonna have a break here. Okay.